Okay, now we just talked about this at some length, by waving hands and using a battery as a current segment. And looking at the magnetic field of a current loop. Now, we looked at it first at a point at the center of the loop, but above. And of course, we could have looked at below, but we're just going to look at the center of the loop right now. Okay, so here's our picture. Here's our loop. It's a badly drawn circle. Attempt to render it in the XYZ coordinate system. Okay, but it's down here in the XY plane. And we're going to partition this loop in terms of theta. Okay. And we're going to have 0 less than theta 1, well, 0 equals theta 1, less than theta 2, less than dot, 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 less than theta I minus 1, less than theta I. I'm confused about theta and phi and I. Okay, less than, and so forth. Less than theta sub n equals 2 pi. Because of course, 0 to 2 pi gets us the whole loop. Okay, yeah, let's say radius A. With current I. Okay, here's our I interval. The sample point. Theta sub I star. And we'll call the length of the theta interval delta theta sub I, right? So, first of all, how long is the corresponding increment of the loop what's I delta L for the increment? And what's the contribution to the magnetic field at the origin? See if you can answer as many of those questions as possible, hopefully all of them. And the camera did stay in focus, but it wanted to zoom back a little bit. Okay, there we got it. Okay. Okay, now I probably should have written the rule up here before I let you ponder. Let you ponder for about 2 minutes, that was enough. Okay, so I got to write the rule as I generally write it. The delta B sub I is K prime times I delta L, where delta L is a vector of whatever length this is in the direction of the current. Okay. You cross that with the R vector, which of course, you demonstrated it. Your right hand was doing all the right things when we discussed it. So I'm not going to. So we have a delta R, we'll call it delta R sub I over the magnitude of R sub I. over r sub I squared. With no vector over the r sub I, we mean the magnitude of r sub I. Now, I could put absolute value signs around that with an arrow over it, it'd mean the same thing. Okay, and I've done that before, but right now I'm going to dispense with the absolute value signs. And I could have done the same thing here. I could have said that that's just r sub I without the absolute value signs or the arrow. But I wanted to emphasize here, you're dividing a vector by its magnitude, which gives you a unit vector. So you have this cross product with the unit vector, which gives you the direction of the field contribution over, well, it's an inverse square distance, right? It falls off as a square of the distance, just like gravitational or electric fields of point charges. Okay. Gravitational fields of point-like masses, electric fields of point-like charges. Inverse square law, here's another inverse square law, but it's a little more complicated because of this cross product, okay? It has a direction that's not as obvious as it is with a gravitational field, which is toward the center, or an electric field, which is either away from the charge or toward the charge, okay? There's your rule. So now, first of all, well, my first question was, what was the length of this increment? So let's talk about that because we can't go very far unless we know the length of the increment. Okay, now I pose the question, what's your delta L? Just, your first question, right? And I said, okay, how are you going to answer that question? I made it responsible. Well, the circumference of the whole thing is 2 pi a. Because it's 2 pi times the radius, and the radius is a. That's a start. That's not the most direct way to get it, but that's a start. Now the next question is, well, how much of the circle do we have here? Well, that goes back to the fact that your interval, your theta interval is delta theta sub I, right? Now, if your theta interval is delta theta sub I, what portion of the entire circle do we have? Now, the process I had to go through to drag this out of you, after you said, well, we know what the circumference is, it's 2 pi a, okay? Okay. Let's work with 360 degrees for a minute. Now we know that's 2 pi, but the arithmetic is easier, 360 degrees. Okay, give me an angle for this loop. That means, what angle is this corresponds to this distance along the loop? Because we want to find the distance along the loop in terms of angles. Okay, that's best specifically in terms of the angular displacement delta sub I corresponding to that ith interval, right? Okay. Now we could say, delta sub I is delta sub I minus delta sub, or theta sub I minus, I said, yeah. Delta theta sub I is theta sub I minus theta sub I minus 1, right? I'm not going to write that up there, but I'll say, okay, we got a delta theta sub I equals theta sub I minus theta sub I minus 1. And we can say, well, we'll use the same delta theta all around. It doesn't hurt to do that. Sometimes it's convenient when you go deeper into analysis to not assume that all these are the same length. But in calculus courses these days, we pretty much assume it. Okay. Not necessary as long as the limit of your delta theta sub I approaches 0. And somehow over the whole partition, and we're going to get into that. Okay, so we got a delta theta sub I now. So okay, give me a delta theta sub I that might correspond to that interval. Well, first answer I got was 120 degrees. Now 120 degrees would be a lot bigger than that interval. Be a third of the circle, obviously, because 120 is a third of 360. And we all know that. We got that immediately. So well, that's okay. It's a little big, but what would you do if it was 120 degrees? What would your length be? So what would be a third of the circumference? Yep. So it'd be a third of 2 pi a. Okay. Or a third of, well, a with your conversion to degrees. We don't really want that conversion because we're going to be doing calculus on that. Okay. But that's fine. okay? Just to get the intuitive grasp. And we need to ask questions like that when we're trying to deconstruct a question that we're not sure of. Now, immediately we saw that, got that answer almost immediately. Circumference is 2 pi a. We're going to use that. We've got to use proportions. Okay, and it's direct proportions. It's simple proportion, but I see that we need to think about that. Okay, so let's do a more realistic, what's a more realistic thing? Well, next thing I got, I think, was 20 degrees. Well, 20 degrees is quite a bit bigger than that, but still we're getting there. Okay, it was probably closer to 10 degrees, but if it's 20 degrees, then okay, now how much of the circle would that be? Well, 1/18th, okay? Because you do 20 divided by 180 or 360. So 360 by 20, you get 18. Now the first one I got was 25 degrees. And I said, that's not a good one because it's hard to divide 360 by 25, okay? 14.4 degrees, but you're not gonna figure that out in your head. Maybe you will, as smart as I am. Probably not as adept at mental arithmetic because they put a calculator in your hand before you could suck a bottle. Okay, first thing you get first thing I put in my hand when I was born was football, because I grew up in a football crazy town with a lot of accomplishments. Okay, probably one of the 2 best in the nation. The other was only 8 miles away. Okay, intense rivalry. Crazy people. The first thing I put in kids' hands these days is a calculator. So I learned to throw a football, not very accurately, but pretty far. Okay, I had a strong arm for my size. I never did learn to throw a calculator properly. So take that lesson for whatever it's worth. I would much rather be good at throwing a football. Not that I can throw anything now that my shoulders are wrecked, but I'd much rather be adept at throwing a football than a calculator, even though I certainly, every time I see a calculator, have the impulse to throw it. Okay. I got to digress the story. Back when calculators first became affordable, this is like in the mid to late 70s, okay? That might have even been in the 80s because I was getting pretty old. I was playing intramural football. I was mediocre. I was competing against guys a lot younger than I was. And I wasn't that good anyway. And my shoulders are already half wrecked, so I couldn't throw a football more than about 30 yards. Okay. Had to throw it a low trajectory. I messed up the shoulder. Anyhow, so I didn't get to play quarterback very often. I still had pretty good hands. So I was almost worth having on the field. Okay. Some of the guys I was playing with were in my class. We had big classes in those days. One of the guys, the smart guy, these guys were going to be engineers and stuff. He's always late for class. And he had this calculator. Now, these calculators cost like $200 in $1980. Okay, that's like $1,000 now. Okay, yeah. His name was Jimmy. Well, one day he left his calculator sitting on the table, so I hit the calculator and took the case and put an eraser in. And he walked into class and said, "Jimmy, I'm tired of you being late." And I threw that thing against the wall. He almost had a heart attack. I'd probably get sued today. I said, "Here's a calculator." Before he killed me, I probably could. I was in a little better shape in those days. He was pretty tough. I don't know what that has to do with physics. There's a proportionality involved in it somewhere. And I don't know how we got into that digression, but here we are in the loop again, okay? Let's get back to reality. The fact that people can't do mental arithmetic very well now, put a calculator in there. You never know where my mind's going to go. Okay, so we're down to 10 degrees here, okay? Which is now 1/36 of the circle. So we take 1/36 of the whole circumference, 1/36 of 2 pi a. Pi over 18 times a. if you want to grasp that. Okay. Now, the whole thing is we're trying to get to the fact that I would almost hope would be kind of obvious in the future to you, that the delta L here is delta theta sub I over 2 pi times A. Okay, so my answer here. I said delta theta sub I over 2 pi times A. It's delta theta sub I over 2 pi, which is a proportion of the whole thing you have, multiplied by 2 pi A, which is the circumference. Now, this is a proportion of your entire circumference. Of course, that's just delta theta sub I times A, right? And you could have answered this instantly if you thought about the definition of a radian. So I'm going to really emphasize to you that you should understand the definition of the radian and why that tells you that this is just delta theta sub I times A. And you don't need the proportionality, although the proportionality will get you there in an emergency, like you forget what the definition of a radian is and how it applies, okay? You don't want to be forgetting the definition of a radian and how it applies. That's just part of your mental machinery as soon as you've had a pre-calculus course. If you've had a good pre-calculus course, which nobody has because of COVID within the last couple of years, including mine, okay? But you just get so much out of students during a pandemic. No excuse for not knowing that though. You gotta, you got to make that up. We can't be producing a sub-generation of engineers who don't know basic stuff. Okay, you got to make this up. If you do, nobody's going to get hired. You know, there's going to be a stigma on the whole graduating class, which concerns me because my grandson is about to graduate next year. Okay. But industry is going to need engineers, and those who have, and people are going to still get hired, and those who've made up their deficiencies will be more likely to keep their jobs or to move up in the, you know, more challenging projects, more pay, okay, and stuff like that. So I kind of, you know, urge you to make sure that you understand these things in perspective. In any year, somehow people don't understand this, okay? But it's still important. It comes up all the time. You want to understand it. Okay, well, end of soapbox, but just an urge to make up some of these things or be prepared to continue having to figure them out as you go. Okay, now let's go on now. What's I delta L for these higher increment? And what's the contribution to the magnetic field? Once you have your delta L, it should be fairly straightforward. Okay. So right there is what your delta B sub I is. Okay. It's K prime times I. And delta L has a magnitude of delta theta sub I times A, right? Okay. Now, delta L is perpendicular to R sub I because delta L is in the plane here. And the R vector is radial from the origin out to the point because we're trying to calculate the field at the origin, right? So this A delta theta sub I times your R sub I is just A delta theta sub I times R sub I over magnitude of R sub I. This is just a unit vector that's perpendicular to delta L. So now you're going to write a reason for it over a square. Okay. And I'll note that Ri over magnitude of Ri is perpendicular to delta L. So the magnitude of this cross product is just delta L equals A delta theta sub I. Okay. Direction is in the positive Z direction. So I'll say it's the direction of the K vector. Because clearly, if you're moving counterclockwise around this loop, every delta L, every R cross delta L is going to be in the Z direction. And again, everybody understands that because your right-hand rule was right on when we did this in the real world. So this is times K. Now this K is not related to K prime. Okay, K prime is related to mu naught, and K prime is a lot easier number to remember than mu naught. Has magnitude 10 to the negative 7th in the units that give you force units when you multiply it by current. Okay. Okay, so there you have it. Well, then what's the sum of all your B sub I is going to be? And I think that's going to take a little room, but it doesn't. Okay, the sum from I equals 1 to n of your delta B sub i's is the sum of K prime I A delta theta sub I over A squared times your K vector. Can you read that? Okay. What factors out of that sum? Okay, now this is important to understand why you don't have to do an integral here, because normally this would, you take the limit as n goes to infinity, as your theta i's shrink down to 0 and everything. Okay, but in this case, you don't need it. K prime is the same for every increment, right? I is the same throughout the loop, so I is the same for every increment. A is just the radius of the circle, which doesn't change. And your K vector doesn't change. The only thing that you have to sum then is your delta theta sub i's. So you can factor this out. It's K prime I over A. I don't need the, A over A squared is just 1 over A, so we could have simplified that at any point. And your K vector is always the same because your direction is the same for every increment. The direction of your magnetic field times the sum of your delta theta sub I. Okay. Now, what's the sum of your delta theta sub i's? Okay, I was relieved that we got a really quick answer on that. Okay. If you add up all your delta theta sub i's, you get 2 pi because your delta theta sub i's is what you use to partition your 2 pi. So you visualize that, you just have little partitions all the way around the circle. I'll draw them all. There we go. That's 1 million, isn't it? Okay. I think I got 1 million in there. I think I did. I'm confident. The less you know, the more confident you are. Tell me what that implies about me. Okay. Okay, but there's 1 million of them. I claim it. I believe it, so it must be true. Okay. If you add up all these delta theta sub i's, you get the whole circle, which is 2 pi. Okay. Or because you partition this, and the partitions, divide the thing up into pieces that add up to the whole thing that don't overlap. Okay. You find that this is this is getting really sloppy here. But there it is. So I'm going to write it a little bigger, but I'm going to write it then. We usually want to write our 2 pi out in front. So I don't want to do the steps in between to get there. 2 pi K prime, which is related to that mu naught thing, right? Like it is. Okay. Times your current divided by your radius times your K vector, meaning just that it's in the upward Z direction. So here's your B prime. And if you want the B from a single increment, let's just kind of make that increment nice and green. Then you got a delta B. Be a lot smaller than that because I've got 1 million of these things. This would only be 1 millionth as long as that. Okay, so it's not really to scale. I could draw up to scale, but I don't have my micro etcher. I don't know. Let's see how close. You wouldn't be anywhere near the atomic scale. That's about 10 to the -1 meter, 10 to the -7th meter. Okay, that'd be 100 nanometers. You could etch that in a chip, it's no problem. Okay, be totally invisible even to microscope, a bit, a light microscope at least, because wavelength light is like minimum 400 nanometers. That's 100 nanometers. Not going to see. It's light. Okay, so of course I can do that because I have really good fine motor skill. Go try yourself. Okay, at least not at home. You get hurt. Now, there we have it. Okay. So this is a delta B, not to scale, because I've got 1 million of these, obviously. You count. Thank you much. Okay, so there's my delta B. There's my B, which is all my delta B's added up. I can put a bunch of these little arrows on it. It takes longer to draw arrows, and it'd take me 5-10 minutes to draw 1 million of them. Okay. Okay, well, there we go. That's the expression. Okay, I'm using K prime. Your book wants to use mu naught. Mu naught doesn't carry the 2 pi around with it. Okay, just like the epsilon naught doesn't carry the 1/4 pi around with it, and the reciprocal and all that stuff. But they're totally equivalent units. And I like to use the K and K prime. Again, because the numbers are really easy. 9 times 10 to the 9 newton squared per coulomb squared. Okay. 10 to the -7th. Okay. Tesla amp per meter, not meter per amp, whatever it is, makes the units work out. I always get that one confused because I don't use it that often. But I know how to work it out. I know what you multiply it by to get what you get. Okay. Well, that was easy. I mean, it really is easy. You really need to know this. Now we want to ask ourselves, okay, what's the magnetic field up here at some point in the z-axis? And of course, if you get off the z-axis, what have you got? Well, what you've got from a current loop is a dipole field. We talked about that the other day, so I'm not going to say too much about it now. Let me go ahead and erase this little blurb. And now really the whole key to getting the field of a loop incidentally, to draw a loop, just to give you a hint, you could really draw a rectangle, not particularly well drawn. And of course, your loop has to be parallel to the sides of the rectangle along the coordinate axis, okay? So you have to have the loop kind of going in this direction. And it's got to curve around and go around here to where it becomes tangent to the rectangle here, or the square actually in this case. And tangent here, and then this is kind of tricky. You got to get tangent here. It kind of retrograde and comes around like this, and it's still no good. Okay? But it's better than it would be if I hadn't done that. Because I probably wouldn't have it perpendicular to the axis, which it has to be because of the tangent line and the radial line for a circle, which should be totally familiar. Okay, so again, we're going to have our typical increment here. Now that's our increment, that's our delta L increment. Okay. And our delta L sub I increment corresponding to theta sub I. Tangent to the circle with length there's a delta. It equals delta theta sub I times your radius A. Again, you got a circle, radius is A. And you got a sample point. And angle theta sub I star. Okay. Now, in terms of that, well, first question is what are the coordinates of this point? Because we're going to need to get our R vector. And we don't actually need it because of what I demonstrated, you know, the TP thing up at the top here. You know, how your magnetic fields kind of do this sort of thing. And we just do that. So I'll explain that in the video when we get to it. Okay, but what we want now is we want the field at a point here. let's just call this point 0. 0 z to emphasize it's on the z-axis. Okay. Okay, well, first of all, well, let's calculate. We're going to use rectangular coordinates. Where's our r vector? Okay, where's our r vector start? What's the direction of our r vector? If the x-axis is south, well, our vector goes from here to here, right? Okay. So here's our sub I vector. Now, where's our current vector? What's the direction of our current vector? Well, it should be obvious that our current vector, if I is counterclockwise, then our I delta L sub I vector is in the plane down here. Okay, it's in the XY plane because it's not clear without some projection lines and stuff where this vector actually would be, but it's tangent to the circle and it's in the XY plane. Okay. So my questions now, we know magnitude of delta L sub I is this order A delta L theta sub I. What's our R sub I vector? Now to get our R sub I vector, you've got to know the coordinates of this point here on the circle at angle delta theta sub I, or at theta sub I star. Okay. Say it right. Point of the circle corresponds to the angle theta sub I star. Okay. So to get this, I said we first want to find the coordinates, rectangular coordinates of our sample point, because our cross product is easiest to calculate in rectangular coordinates. The entire board wasn't clear, but enough that all this was, so I think we're okay here. So what do you think? What are the coordinates of that point? You understand how this is the critical piece if we want to do the cross product of your delta, your R sub I vector with your delta L sub I vector, right? Your R sub I vector would be like this, your delta L sub I is like this, it's your cross product. Yeah, you should be able to visualize where it's going to be, and I think you can because you're good with that right hand stuff. Okay. But then what's the mathematical representation of that R sub I vector so that we can do a cross product? Although in a good workout, you do get exhaustion. Well, in a mental workout, it doesn't work as well. Not as much benefit once you get exhausted. Okay, so I'm going to redraw this circle, but I'm going to put the x-axis this way and the y-axis this way. So I just, looking down on this, I just rotate it 90 degrees to make it look like this, right? And where I've got my theta sub I over here, well, let's see, I did it dumb. Let's draw a square here and see if I can draw a decent circle. That's not too bad. Okay. Maybe I ought to do that more often instead of drawing them free down. I've got to where I can do that pretty well, but it's unreliable. Okay, so anyhow, our picture here looked at from above with our head oriented, so the x-axis is this way, y-axis is this way, right? So we're looking down on it here, our nose is pointing down, our forehead's pointing that way. Okay. It's gonna look like this. Here's your theta sub I. Here's your increment of length L theta delta theta sub I. Okay. And here's your point. And this is not theta sub I, it's theta sub I star. Okay. The theta sub I for your sample point within the ith partition, or the ith increment of the partition. So what are the coordinates of this? What are the rectangular coordinates of this point? Okay. So that I can put it together with the rectangular coordinates 0, 0, z of the point at which I'm calculating the magnetic field and do a cross product. Also, while we're at it, where's delta L sub I? Well, it's in the plane of tangent to this. So here's your, did I say that right? Yeah. Here's your I times the vector delta L sub I, which is perpendicular to this thing, okay? So let's try to get both expressions for the coordinates of this point, which we need so we can do our R vector. And this, so we have the vector to cross with that. Okay, once we've got that, we're almost home free because there's a symmetry argument that simplifies everything. And of course, we plug it into our K prime I delta L cross I, that cross R, R cross. You know, did I write that wrong? Oh man, how could I have done that? Well, I did something really boneheaded here. You know, it's R cross I delta L. No, it isn't. Yeah. No. What did I say about mental exhaustion? Okay. I'll get it straight and say something in a minute, but okay. We're going to plug this into the form. All you need is your I delta L vector and your R vector, and everything else falls right in your lap. In a nice way, we'll see how it works. Okay, so again, coordinates of this point and this vector. Now we're tending to confuse the I delta L and the coordinates of this point, okay? One question at a time. The coordinates of your sample point, that's just one point on the circle. It's located on the circle at angular coordinate theta sub I star. So I want to know what are the coordinates of that point. Has nothing to do with how wide the interval is or anything. This is a sample point, one point on the circle. Now, once you have the coordinates of that point, it's going to help you figure out what the direction of your delta L sub I is. It's going to be perpendicular to this vector from here to here. Okay. It's going to be tangent to the curve, but that's a separate question. First question, what are the coordinates of the sample point? Okay, when you finally focused on it, you got it pretty quickly, okay? But I would write the slide today in history. I'm writing something profound here. And you guys have been saying sine before cosine, but you said it right. You said it right. We finally got to them too. It's A cosine theta sub I star. Matched by the circular definition of the sine and cosine functions. Now, you pretty much have that definition, okay, but you got to get better at applying it when it's relevant and seeing it when it's relevant. Just like you've got to see triangles to solve a lot of problems in physics, okay? A lot of problems in higher, mononomial calculus and stuff. You got to see those things in order to efficiently use them. So you know the definition. And when I finally narrowed you down to focusing on this point, you were able to apply the definition, okay? But of course, when you understand this picture, you want to see that immediately so that you can move on and build integrals on it and stuff like that. And that's a work in progress. Nobody's inherently good at it when they first see it. At this stage, you should be maybe a little better doing it, but just being able to do it is not there. Okay. Okay, so there we have it. Anyhow. Okay, there's your circularly deficient. Okay, that's a lot like a definition, but it's a shortened term. So definition. There we got it. That I is double potted. That's okay. Okay. If I can leave a silb out of definition, you can miss something that obvious once. Don't look again. Okay. It's not totally obvious because it's there in the booming, buzzing confusion of this whole problem. So it's not that confusing once you see it, but when you first try to work it out, yeah. Okay, so now what is the direction of this thing? I just realized over time, if you got to go ahead and take a look at the video when it's posted. Okay, well, I'm going to finish it for you. Okay, this is perpendicular to this. Okay, which means that the sine and the cosine are going to have to be reversed. So it's either going to be your delta L or your I delta L times the negative sine, cosine, or times the sine negative cosine. Okay. Now, which is it? Well, right about. Okay, it's either going to be, well, I'm going to first write sine theta sub I times your I vector, and your cosine theta sub I times your j vector. Okay. Now, one of these is going to be positive and one's going to be negative, and it's going to be the same no matter what quadrant this is in. Positive and negatives will go the way they do. So in this picture, is the I component positive or negative, and is a cosine positive or negative? Well, let's be, okay. First of all, the sine of theta sub I is positive, the cosine is negative here. And they're both negative here. Okay. Since the cosine is the negative one, the negative of the cosine is going to be a positive, and it's going to be negative sine theta sub I plus cosine theta sub I. And there are other ways to see that. Slope's got to be a negative reciprocal and all that stuff. There are plenty of ways to see why that is. I'm not going to get rigorous about that at this point. So that okay. So we got one of the vectors that we need to do the cross product. Now the R vector is just, if you wish, the vector from here to here minus the vector from here to here. It's where you end up, minus where you start. And that's just this. Now, what's the cross product of this vector with this vector? Okay, well, you can use a distributive law. You can write out the determinant thing if you want. But it's just going to be negative sine theta sub I crossed with, well, crossed with this, but this is a multiple of I, and I cross I is 0. This times this, well, you're going to have I cross J. Okay, I cross J is K. Just right angle. And you're going to have two negatives here, so you're going to have A times the sine squared of theta sub I star. Okay. Now you're also going to have a component from this cross product with the J. I mean, I just said that, so I don't know what I'm talking about. With the K. Okay. So I cross K. I cross K is negative J. You got a negative there, a negative. Well, you put it all together and you get the cross product. The cross product is going to give you a component in the Z direction. And all the other components are going to cancel out because they're all going to be in the XY direction. And by symmetry, the component you get from this is going to have the same Z component as what you would get from a segment on the opposite side of the axis or of the origin to reflect this segment through the origin. Okay. Then your B vector is going to have the same Z component. It's going to have the opposite component in the XY plane. So the XY components will cancel out. You're going to have, you know, your picture is going to kind of look like this around the Z axis, and that's really bad. That missed that, but you get that TP effect, and everything in this direction cancels everything in this direction, leaving you just this direction. So you really only have to worry about the Z component of what you get when you do this cross product. Now I want you to work that out. Okay, see if you can work that out for next time. Okay, don't know if I said it on screen, but you know, at this point, we're 10 minutes over time. Don't want to keep you any longer, but at this point, you ought to be able to work it out. Okay, and if you write out the summation, write out all the details, pretty much everything except the sines and the cosines and your Z component. Well, your Z component is always the same. Your sines and cosines, the I and J components of your cross product are going to, by symmetry, cancel each other out. You're only going to end up with the K components, and that's what you end up integrating. And really, you don't even have to necessarily do an integral, but it's good for your soul to write out the integral.